Hi everyone, this is a video for section 2.8, which is called Graphing Linear and Absolute Value Inequalities. And I think it's going to be pretty straightforward for you because you have some background in both linear and absolute value equations and how to graph those. So the first thing we're going to just quickly talk about is what the difference is between linear and absolute value equations and inequalities. The big thing here is that we're going to deal with greater than, less than, greater than or equal to, and less than or equal signs in our examples, which means that our boundary line, we're going to have what's called a boundary line, is going to be the basic graph. And we need to determine if it's going to be dashed. And if it's dashed, that means we have greater than or less than involved, or a solid line, and that means that our inequality would have greater than or equal to or less than or equal to involved in it. The other thing is that we have to pick a region to shade. So all of these graphs are going to have shading involved in them. You'll see from the first example that I do that it's not overly challenging. You have to do just a little bit of thinking as far as which region to shade. So we're going to jump right into examples because I don't have to give you a lot of background on this. The first example says graph the linear inequality. Now I know that this is linear because it doesn't have an absolute value in it. It fits the idea of a linear equation, except the only difference is it has an inequality symbol in it. So the easiest way to graph a linear equation, remember, is to put it in that y equals mx plus b form. So I'm going to manipulate this so that it fits the y equals. Now I'm using equals and I'm saying equals, but when we work with this, it will have an inequality symbol. The mx plus b form. So we're going to isolate the y, which means if I take x plus 4y is greater than 2, I'm going to subtract x from both sides and end up with 4y is greater than negative x plus 2, which means that y is greater than, I'm going to divide everything through by 4. So negative 1/4 x plus 1/2 as I do my division by 4. This means that the y-intercept of this graph is 1/2 and our slope is equal to negative 1/4. So this is considered to be the equation y equals negative 1/4 x plus 1/2 is my boundary line. And I have to make a decision if this boundary line is going to be a solid dot or a solid line or a dashed line. I'm going to check my inequality symbol in the original problem, and because it's just greater than, it's going to indicate that this is going to be a dashed line. So I need to connect my dots using dashes instead of a solid line. So I'm going to go up to 1/2 from my y-intercept, and I'm going to move according to a slope of negative 1/4, which means I will go down 1 unit and to the right 4 units. So my next dot will be here. And I'm going to move 1 more in the other direction just to make sure that everything lines up. I would go up 1 unit from my original y-intercept and to the left 4, which will plot my point here. Now, I don't have a ruler. You can use a ruler at home to make this a little bit more accurate. But we're going to connect these dots with a dashed line. This is my dashed boundary line. I want, in this problem, it says all y values greater than my boundary. So I'm going to go to where my graph hits the y-axis. It hits the y-axis at 1/2. Where are the y values that are greater than 1/2? Well, they appear in this region. Greater than is the higher part. So that means I'm going to shade the part of the graph that falls above that y-intercept. So all of these values would satisfy this inequality. Y is greater than negative 1/4 x plus 1/2. And that's the end of it. We're going to label our boundary line as y equals negative 1/4 x plus 1/2. But overall, this is the graph of y is greater than negative 1/4 x plus 1/2. I could label it with it the original graph too, x plus 4y is greater than 2. Those labels would be acceptable. And that's it. So it's not too complicated. We just have to make sure that we follow all of the inequality rules when we put things in good form to graph. So if you have any questions on this, make sure that you make a note, and I'm going to move right into the next example. So the next example, again, is linear, and I know that because of the form that's presented to me. There's variables, but they only have powers of 1 on them, and it's no absolute value symbol involved. So I'm going to manipulate this into the y equals mx plus b form too. I'm going to isolate the y. I need to get y by itself. So the first thing we'll do is move the 3x to the other side, and that will leave us with 1/2 y equals, oh, not equals, see, I'm falling right into the trap here, is less than or equal to negative 3x plus 2. Now to get y by itself, I'm going to multiply everything through by 2. So if I multiply both sides by 2, that's going to leave me with y is less than or equal to negative 6x plus 4. This is the inequality that I want to graph. And my boundary line, remember, is y equals negative 6x plus 4. I have to make a decision if it's dashed or solid. And in this case, because the equal bar is involved, it's going to be a solid line. And then I'm going to graph it and figure out which region to shade. So 4 is my y-intercept. 1, 2, 3, 4. My slope is negative 6, which means I will go down 6 into the right one. I don't know if I have room to go up 6. 1, 2, 3, 4. I have exactly 6. To the left one. This time it's a solid line. My lines aren't going to be perfect because I'm doing this on the smartboard. And I need the y values that are smaller than or equal to this line. Now, I know that the equals are already done because it's a solid line. So I'm going to go to my y-intercept. I'm going to figure out where the y values are smaller, and that's this region going down, which means I'm going to shade everything to the left of this graph. And that would be my solution set. That means that any ordered pair that falls in the shaded region, so say I pick this ordered pair, which would be negative 3, negative 5, 2. If I sub this value into the original function, 3 times negative 5 plus 1/2 times 2, that should turn out to be smaller than or equal to 2. So negative 15 plus 1 is less than or equal to 2. Negative 14 is less than or equal to 2, which is a truth statement. So if I picked a point out here, say the point 2, 0, and I tried subbing that in, 3 times 2, so this is 2, 0, plus 1/2 times 0 should be less than or equal to 2 if it's a correct answer to this. Now we're hoping it doesn't work out because I didn't shade that part. 6 is less than or equal to 0. So that's not true, which means that I picked the right region to shade. So you can do a check that way algebraically if you so choose. But that's really what these graphs are showing us. Anything in this area over on this side would be a solution to this problem. Now, one thing I'm going to make you aware of as I go through and I take everything off of this screen is that we have to follow all the rules of inequalities, which means if we ever have to multiply or divide through by a negative value, we have to remember to switch the direction of the inequality symbol. I'm going to go through and do a couple absolute values for you, and then we'll be all set. So this one is y is greater than or equal to the absolute value of x minus 4. Now, we've talked about this parent function, y equals the absolute value of x. And we know it looks like a v with its vertex at 0, 0, and a slope of 1 in either direction. A slope of 1 going up in the positive and then negative 1 on the other side. This graph, though, according to the last section that we studied with our transformations, is going to move down 4 units. So that means that I'm going to look at graphing y equals the absolute value of x minus 4 and make a decision because it's got an equal bar in my inequality symbol that this will be a solid line. So my vertex is at negative 4. I didn't move anywhere horizontally, so it stays along the y-axis. And then I'm going to move according to the idea of the absolute value function. So I'm going to put a few of the points on here. It's solid, which means I'm going to connect my dots. And this is the general shape of my graph. So this is, I don't think I labeled that last graph, did I? This is the equation y equals the absolute value of x minus 4. We want to shade so that our solution is showing y values that are greater than or equal to. We've done the equal part. Again, I'm going to go to the place where the y-intercept is, and I want values that are greater than that y-intercept. So greater than that y-intercept fall in this region, which means I'm going to shade everything inside the absolute value. So as this absolute value keeps continuing, now I have arrows here, but I didn't draw it all the way out on the graph. As it keeps continuing, only the points, the ordered pairs that fall inside of the V, would be part of the solution set. We don't write all those values down because there's an infinite number of values, and that's why our shading, basically, our graph is our solution to that problem. So let me know if you have any questions on it. The big twist here is that this is now absolute value instead of a linear function, and we make a determination basically if we shade inside the absolute value or outside of the absolute value. But we can do a couple more in class together if you have any questions on them. Then I just have one more for you, and we'll be good to go. Let's see. This one is y minus 3 is less than the absolute value of x minus 3 plus 4. You know what I think I'm going to do? I think I'm going to, no, let's leave it like this, and we'll talk about one together in class a little bit later when I see you next. So in this problem, I need to isolate the y again, because remember, the y has to be by itself. So this minus 3 is standing in the way. I'm going to add the 3 to the other side, which gives me y is less than the absolute value of x minus 3. When I add this 3, it gets added onto the 4. I can't add it inside the absolute value sign. So it becomes plus 7, which means that my vertex is now at the point, because this graph went to the right 3 and up 7 based on my translations. It went horizontally 3 units to the right. It went vertically up 7 units. So my vertex is going to be to the right 3, 1, 2, 3, and up 7. So it's going to be right here. Now this slope is the same as the other one. So I know that my V is going to hold the same shape. And it's going to be a dashed line, though, because the boundary doesn't include, it doesn't have an equal bar. So I've got to carefully connect and make sure that these are connected only by dashed lines. So my absolute value looks like this. This is really y equals the absolute value of x minus 3 plus 7. The dashed line is indicating that I don't want every value on there. I want everything but that. And I need to shade anything that's smaller than the y value that I have. So I'm going to the y-intercept. Now the y-intercept is right here on this one. It's not at the vertex because it made a horizontal shift. I want to shade everything smaller than that y value, which is down. So the entire outside of this graph is going to be shaded. I'll do a crosshatch for this one so you get a good idea of what's going on. And that would be my solution set. So anything outside of that absolute value in a boundary would be a solution set to my problem. That's about it, guys. As you get a little bit more advanced with things, we can do these with parabolas, and maybe we can even try some together in class. But this is the basic gist of it. Boundary lines, dashed or shaded, or dashed or solid, and then determining which region to shade once you get your functions in their basic graphing form. So if you have any questions for me, let me know, and we can answer those together in class or shoot me an email. And then when I see you next time, we will do some work with these. So thanks for listening. See you next time.